Hey everybody, this is the video I'm making for chapter 10, which should end the chapter and therefore be the last bit for unit 3 here. We left off in class here at oxygen's molecular orbital diagram. Now, I will remind you that these pictures are for molecular orbitals, and for oxygen, it has an electron configuration of 1s2, 2s2, 2p4. So you get that valence shell of oxygen atoms by themselves, and you can see the 2s electrons and the 4p electrons there. Zooming in, 2p, 2s. Same on the other side for the other oxygen atom, and those electrons, represented by the arrows, will fill into the molecular orbital diagram for molecular oxygen there. We can ignore the core electrons because they will always fill up and complete the core electrons, molecular orbitals, just like these will. In the 2s section, we have the sigma 2s, the sigma 2s star, also known as just the sigma star, and sigma, the bonding one in the bottom, the anti-bonding at the top for oxygen. And then over here we have 2, 4, 6, 8 total electrons. And those fill into the molecular orbital as such. 1, 2, 3, 4, 5, 6, 7, 8. So when we look at the bond order for oxygen, and I know we did this in class, but it was at the end, and I'm just going to repeat it. We have 2, 4, 6, 8 bonding electrons minus 2, 3, and 4 anti-bonding electrons, which means that it has a bond order of 2. So I'll remind you that oxygen has this Lewis structure, and it has a double bond, and the bond order is 2. The problem is that oxygen is a diradical, meaning those two electrons in the pi star, the pi anti-bonding orbitals here, those are not paired. They're radicals, so they're actually highly reactive. You can't make a drawing of oxygen in a Lewis structure that has the diradical. So nitrogen, for example, had this Lewis structure, and nitrogen has one less electron. It's, I'll just do it over here. It's 1s2, 2s2, 2p3. So we get rid of this electron there. You get rid of this electron here, which means both of those are gone. And so the bond order for nitrogen is 3, and you get the Lewis structure matching it. Nitrogen is a gas. It boils at 77 Kelvin. So it's not, what that means is that it's not polar at all. The electrons are not utilized to, let's say, stick to anything, whether it's itself or anything else. And that's why it's, it boils at such a low temperature, because it's completely non-polar and it doesn't have electrons to use, whereas oxygen does. Now, oxygen is a gas at room temperature too, and it boils at 96. It's a little bit more massive than nitrogen, by a small fraction. It weighs more, but it's higher in its boiling point than nitrogen because it has the ability to use those electrons. Furthermore, we breathe in oxygen. Oxygen has these, 2 radical electrons it can use to attach to something like iron in your hemoglobin in your blood, which has a 2+ charge, whereas nitrogen, although it has a lone pair, they're paired. They're not radicals, so they're less likely to be used. So there's really nothing on Earth that breathes in nitrogen, and very few organisms at all can even use nitrogen for anything. The ones that can are called nitrogen-fixing bacteria, and it's like one thing on Earth, out of the millions of different species that can actually utilize molecular nitrogen. And again, lots of things use oxygen because it has these diradicals, so they're actually usable. What are the MO diagrams for O2 plus and O2 minus? What is the bond order for each? Which has the strongest bond? The bond order and the strongest bond are going to go hand in hand. So the higher the bond order, the stronger the bond, and vice versa. For O2 plus, since the oxygen molecule has lost an electron, we delete one of those out, leaving the other in. All right, so this is what the electrons would look like. It doesn't really matter which of these electrons you delete, but it ends up filling into the molecular orbitals as such. So now we have 3 plus 4 for 7 electrons. 1, 2, 3, 4, 5, 6, 7. All right, the bond order for O2 plus would be 2, 4, 6, 8 minus 2 and 3, and you divide that by 2. And so this is 5 over 2, which means it's 2.5. Now, something like O2 plus can exist. Drawing half of a bond is not something we can do. All right? I'm going to highlight here the fact that these electrons and those electrons kind of cancel each other out as bonds, bond and an antibond. So those can be like lone pairs of electrons. So you get lone pairs there. And then you've got this radical electron there. It's not a diradical because there's not two of them. It's just a monoradical, or just simply a radical. All right, so that's kind of canceling out like one electron there. It's not a diradical, but again, this is not something we can draw. We could maybe draw a half of a bond with like this dash thing in there. All right, but then you could put the single radical electron on one of the oxygens, but not the other. And so you can't make a picture of it. And that is the key thing, is that this is not an intuitive way of looking at it. It is realistic, but quantum mechanics, these are weird things, and it's just something you have to accept, that we can't make drawings for these things that are ultimately just mathematical. All right, O2 minus, it would have the bond order of, well, now we've added an electron from the base electron configuration of O2. So now let's add one right here. All right. And this was oxygens there. Now I'm adding one, it'll go over there. And so we have, again, 2, 4, 6, 8 bonding electrons minus 2, 4, 5. And dividing this by 2, so we get 3 halves, or 1.5. Again, for O2 minus, that means there's at least a single bond. We've got these being lone pairs. We've got a lone pair here, but which oxygen do I put it on? Remember, this is delocalized, so it's actually on, all of these are on both atoms, but in the Lewis structures, you try to indicate them being on one, so it's not realistic. And then there's a radical. We have 1.5, so if you did something like this, you'd have, the half bond there per se. But if you just add up the electrons, there's 2, 4, 6, 8, 11, and oxygen O2 has 12 electrons, plus we're adding 1, so it's only showing 11 out of the 13. For this structure in O2 plus, there are 11, and we see 2, 4, 6, 8, 9. So again, these drawings don't match the number of electrons. They're just not the best drawings. But what is the strongest bond? The strongest bond is the O2 plus. So coincidentally, O2 plus has a 2.5 bond order. Oxygen itself, that's neutral, has a bond order of 2. So the strongest bond is in O2+. That does not mean that this is stable and exists, readily in nature or anything, but it could be. All right, next we have fluorine. So the element fluorine has an electron configuration of 1s2, 2s2, 2p5. You see the 5 electrons there, the 2 electrons here, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for the P section. So the bond order for fluorine, you've got 2, 4, 6, 8 electrons in bonding orbitals again. You've got 2, 4, 6 electrons in the antibonding orbitals. You divide it by 2, and it comes out to a bond order of 1. The Lewis structure for fluorine we've already seen looks like this. We can count up the number of lone pairs. We're going to have a lone pair here and there. That's 2, 3 and 4, 5 and 6. We have essentially 1 bond that's left over from there. And again, we have 1, 2, 3, 4, 5, 6. So this Lewis structure does match what the molecular orbital diagram is giving us. All right, now the molecular orbital diagram for NO, nitric oxide. All right, so nitric oxide, if we go back, nitrogen is in group 5. Oxygen is in group 6. There are 11 electrons. All right, so if we draw out the possible Lewis structures, we'd start with the single bond between the 2 atoms. So each atom has a single bond, therefore 3 lone pairs. Counting up the electrons, we get 2, 4, 6, 8, 10, 12, 14 electrons. So that's 3 electrons too many. So if I go backwards here and make it a double bond, you have 2 bonds, 2 lone pairs on each atom. So 2, 4, 6, 8, 10, and 12 electrons. Again, we have too many electrons. In this case, 1 too many. So we could go to a triple bond and see what happens there, but you should know the result beforehand. 3 bonds, 1 lone pair. Counting them up, you've got 2, 4, 6, 8, 10 electrons. So that has 1 electron too few. So it's not either the double or the triple bond. All right. We had, let's go with a double. That's 2, 4 electrons, 6, 8, 10, and 11. You have a radical, a double bond and a radical, and you could, and I accidentally changed the color to red, but you could switch this to having the radical on the nitrogen. 2, 4, 6 electrons there, 8, 10, and then 11. And let me make this consistent by making those black. All right, so either of those would be the appropriate Lewis structures. Neither one is necessarily better. I mean, well, we could look at formal charges. So I should actually do that. The formal charge of the nitrogen here, you have, it's in group 5. And so it'd be 5 minus 1, 2, 3, 4, 5, and 6. So the nitrogen would be a negative. The oxygen is in group 6 and be 6 minus 1, 2, 3, 4, 5. So it ends up as a +1 there. And then overall it's neutral, which is good. In the other resonance structure, you've got 5 minus 1, 2, 3, 4, 5. So that one's 0. And then 6 for the oxygen, minus 1, 2, 3, 4, 5, and 6. So again, that one is neutral. So this is a better resonance structure on the right than the one on the left. But let's go to the molecular orbital diagram for NO. We've got 2, 4 from those electrons. All right, and then we've got 3 plus 4 is 7. Again, it does add up to 11. So 1, 2, 3, 4, 5, 6, 7. Now the bond order for NO is going to be equal to 2, 4, 6, 8 minus 2 and 3. And so it's actually 2.5 bonds. Remember, the double bond didn't work because it gave us this radical, or it had 12 electrons. The triple bond didn't work because it had 10 electrons. It's actually a mixture of the two. It's not a double or a triple bond. It's a 2.5 bond. So in reality, you could draw it with, here's a double, there's the half bond. All right, we've got 1 and 2 lone pairs. And then we've got the radical. Let's put it on the nitrogen. Count up these electrons. There's 2, 4, 6, 8, 9. You can't really count the dotted bond as anything. All right. So again, the pictures, there's no good picture for these things. But these are good enough, but it doesn't match the bond order. How do we know that it doesn't match the bond order? If we had a nitrogen-oxygen single bond versus a nitrogen-oxygen double bond versus a nitrogen-oxygen triple bond, and then I add into here this 2.5 thing that I drew, those different bonds are going to have different bond lengths. And the length of this NO bond that's got a bond order of 2.5 versus a 2.0 versus a 3.0, the bond is going to be shorter than a 2.0 bond and longer than a 3.0 bond. All right, if these are the bond orders there. So the higher the bond order, the shorter the bond. And so you can get structures that have any of these different actual, bond orders. I'm not trying to represent molecule of just being NO, but these within other structures, like maybe there's stuff attached to the nitrogen. The length of the bond does correlate with the bond orders you get. And so NO with a bond order of 2.5, again, would have a length of that bond in between these ones. Okay, so now for NO+, we lose 1 electron. Let's take it away from the oxygen there. And again, we just fill it in. Now we have 6 electrons in the p orbital, so 1, 2, 3, 4, 5, and 6. The bond order of NO+ now is going to be 8 minus just 2 antibonding electrons, and so you get a bond order of 3. So NO+ should have a triple bond. If we go to its proper Lewis structure, again, nitrogen has 5 valence electrons, oxygen has 6 for 11, but because there's a positive charge, we subtract 1 to bring it down to 10 electrons. If you count the electrons here, we've got 2, 4, 6, 8, and 10 electrons, so that one is good. All right, cyanide, Cn-. All right, we have carbon in group 4, nitrogen in group 5, and there's a negative charge. So again, we have 10 electrons. The drawing for the cyanide ion would be the same. And I should have done that with the brackets and the charge outside of the NO+. And I'll do that now for you there. That's what that would look like. The cyanide, because it has the same number of electrons, it has the same structure. And we see that because you have this minus, we're going to add 1 electron into there. So 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6. So again, the molecular orbital diagram for Cn- matches its Lewis structure. All right, next, what if the elements are not similar? This would be a heteronuclear diatomic molecule, HF. Heteronuclear, again, meaning there's different nuclei, in other words, different elements, and it's diatomic. There's 2 atoms in the molecule. Well, if you look closely at this, we have the hydrogen atom on the left, the fluorine atom on the right. Hydrogen has an electron configuration of 1s1. Fluorine is 1s2, 2s2, 2p5. You might expect that, energetically speaking, that these would be way higher in energy than the 1s for the hydrogen. But it turns out not to be true, because it actually turns out that fluorine is a pretty small atom. In fact, it's in some regards smaller than a hydrogen atom in some measures. In other ones, it's pretty close in size to the hydrogen, but maybe slightly bigger. There's many ways that people look at sizes. But it turns out, you look at it, these 2p electrons are, in fact, lower in energy than the 1s. All right, we could talk about the shielding effect and all that stuff, but we're not going to. If you were given an example like this, you see that these 4 electrons are just going to go into the middle of this, which those are non-bonding orbitals. We haven't seen that. There's an anti-bonding over here, and then there's a bonding right here. Because these other ones are in the middle, they're considered non-bonding. And they're of the same energy that they started in. So they're not involved with bonding. This electron is going to go into there. That electron from the hydrogen is going to go in there. And again, we're getting a bond order in HF of 2 bonding electrons minus 0 anti-bonding. So it's 1. The drawing for HF will look like this. Now you have technically here 2, 4, 6, 8 electrons being shown, but we only have 2, 4, and 6. Where's the other 2? Keep in mind the fluorine also has the 2s somewhere down here, and therefore that would be the other lone pair. It's not involved with bonding. There's nothing overlapping here because the 2p section for the hydrogen is overlapping. The 2p section of the fluorine is overlapping with the 1s part of the hydrogen. Now, it's issues like this where you have different elements and the electrons and everything get all weird that lead to molecules being polar. All right? You'll notice that this is not degenerate with those. Everything we've seen so far. Okay, so because there's a difference in these energies for the hydrogen and the fluorine atoms and their orbitals, you can see that the occupied bonding orbital is closer in energy to fluorines than it is to hydrogens. That leads to the electrons, in a sense, existing more near the fluorine atom, and then that leads to fluorine being more electronegative than hydrogen, and therefore you get the polar molecules where the fluorine is partially negative and the hydrogen is partially positive. So the sigma molecular orbital containing the bonding electron pair shows greater electron probability since it is closer to fluorine. Thus, the electron pair is not shared equally. This causes the fluorine atom to have a slight excess of negative charge, making it a partial negative, and leaves the hydrogen atom partially positively charged. This is exactly the bond polarity observed for HF. All right, now resonance structures and molecular orbitals. Consider ozone. We had ozone with these 2 resonance structures earlier and their respective formal charges. If we put the lone pairs in to make it complete, you could add those up and you'd get those. Now, oxygen, these are all oxygen atoms in ozone. So you think, well, if I just take this, that's not what I was trying to do. If I just take this piece out over here, all right, and then I flip that, watch this. I do that, and I put it over here, you see they're exactly the same. So you might think, well, these are the same thing, so they're not really different resonance structures. But it turns out, all right, if I make this oxygen an oxygen-17 isotope and the others are the more common oxygen-16, oxygen-17 is radioactive, so you can measure its radioactive decay relative to where it is. You could measure the hybridization of the atoms. This is sp2, this is sp2, and this is sp3. Now if we take that object, I'm going to make another copy just because it now will be one complete object, and I flip that, then actually let me finish this. These should be the same over here. You see sp2, sp2, and sp3 hybridizations. Now if I take this picture and flip it left to right, I know the letters are all backwards, but you can see that we have an oxygen 16 isotope here that on the double bond that's sp2 hybridized, whereas the other one was an oxygen 17. So it actually is different. And so we're going to look at the molecular orbitals for that. All right, in these molecules, it is the pi bonding that is most clearly delocalized. The sigma bonds will therefore be localized. So in a sense, we can ignore the sigma bonds while really only looking at the pi bonds. P orbitals perpendicular to the plane of the molecule are used to form pi molecular orbitals. Go back earlier in the chapter, all of the pi bonds we had were perpendicular to the rest of the orbitals, and above and below the axis connecting the electrons, parallel p orbitals create pi bond kind of thing. The electrons in the pi MOs are delocalized above and below the plane of the molecule. All right, so delocalization here just means that the electrons are spread out through the entire molecule. And I've been saying that for this whole chapter really, that the electrons are spread out. They're waves. They're spread out through the whole molecule, not just the atom. This is always the case. Now we're going to finally have a picture that kind of shows what that means. All right, so we have the 3 oxygen atoms in ozone here on those pictures on the left. They each have a p orbital that are parallel to each other. They could all 3 be in phase with each other, creating 0 nodes, which creates this bonding molecular orbital. You see a pi bond here. If we have 1 node, then you'll see there's no connection between the 2 orbitals that are on those external oxygens. Because there's no connection between them, and this middle one doesn't even have any orbitals there, we get 1 node through the center of the molecule, and it's considered non-bonding. There's no overlap, so there's no destructive interference there, but they do have the opposite phases near each other. With the next one, now you have each atom with the p orbitals here being out of phase with each other. So you get 2 nodes between the atoms that way, and you get that being the anti-bonding orbital. All right, so this is following the law, the linear combination of atomic orbitals, meaning we have the atoms with 1, 2, and 3 atomic orbitals, that those p orbitals in the molecule create 1, 2, and 3 molecular orbitals. It's always going to match. All right. So again, if we take 3 atoms and I just put them, no phases or anything, we have the different atoms here of oxygen. These are p orbitals. They're going to combine destructively, constructively, and in this case, in a non-bonding way. All right, so you can imagine the different possibilities would be plus, 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 maybe plus, plus, minus, and looks like you'd get 1 node, but in fact, you'd have some bit of bonding right here between these and 1 node, and that's just not how it works. So instead, the middle one ends up doing nothing, and the node now gets shifted to be in the middle, which I can't do because it's all connected as one image. So I'm just going to leave it like that, and you get this drawing there, or you could have plus, minus, plus. All right, now, if you wanted to be like, well, what about minus, minus, minus? That's the same thing as the plus, plus, plus. All right, so those are the only three possibilities of the orbitals that you can get from that. So the drawing of ozone here, going back to it, this is one of the resonance structures. We have that. Now here's oxygen. It's 1s2, 2s2, 2p4 again. We've got 3 of that, right? This has 2 plus 4 is 6 electrons. 6 times 3 is 18 electrons. This is only accounting for 4 electrons out of the rest. All right, so we have 14 electrons outside of the structure we want to look at. Now, if I'm drawing, okay, so we have 18 minus those 4 leaves us 14 electrons. If we were to try to draw the other resonance structure from here, we might take, let's say, those 2 electrons, move them over here, moving those 2 electrons over here to create this, where these and those would be the electrons that are changing. That's 4 electrons, all right? So let's take, let's use those 2 and that as the only point of difference. So I'm going to redraw the structure here. And count up the electrons. We get 2, 4, 6, 8, 10, 12, 14. And then we've got 16 and 18. Those are the ones that are involved in this resonance or in these delocalized molecular orbitals. All right, we have a non-bonding pair, a lone pair, and then the bonding pair, which is the pi bond over there. As a result of all of this, because it switches between the atoms, like where these 4 electrons are going, what we're going to say is, because this is a delocalized model, I'm only going to connect these with single bonds right now. All right. And then we've got the 1, 2, 3, 4, 5 lone pairs. So let's make 1, 2, 3, 4, or 1, 2, 3, 4, and 5. All right, again, that's counting for 14 electrons. 2, 4, 6, 8, 10, 12, 14. Now the other 4, in the proper drawing for this, again, I could put a double bond here, or I could put the double bond there. And that would also switch the location of the non-bonding pair. What I'm going to do instead, though, is draw a arch over there, saying those 4 electrons are really spread out between all 3 atoms. All right. In this Lewis structure, we had a negative charge on the right atom. Over here, it would be on the left. And the middle one gets a positive charge in either case. So in this, we get the positive always in the middle. And it turns out partial negatives on the external ones. Now, if we counted the electrons, there's still 2, 4, 6, 8, 10, 12, 14. And let's say that's 16. That's the bonding pair. We can't draw the lone pair that's from the non-bonding orbital in there. So again, these Lewis structures are just not perfect. There's no good way to do it. But again, let me get rid of all these highlights. This is the best drawing we can make, where you're getting partial negatives on the external ones, the positive in the middle one, and then bonding electrons spread out on all 3 atoms. And it's not like it switches back and forth. It's not going from here to there, which is why we call them resonance structures, because we theorize they could have done that. That was disproven with this molecular orbital theory, in that it's really the mixture of them all at the same time, and it's always this. And it turns out the bond length for these is always the same. It's not a single bond between them. It's not a double bond. The bond orders are all 1.5. for there and here. And so the lengths of the bond are in between a double and a single at all times. So again, we get the orbital diagrams that look like this: bonding, non-bonding, anti-bonding. And just keep in mind, this is strictly for the pi bonds or pi electrons, nothing else. We have pyridine here with this structure. Each corner of that hexagon represents a carbon atom, and the carbons must have 4 bonds. You'll see structures like this in organic chemistry a lot, where we just leave out the carbons and the hydrogens because it's just simpler to do. But anyways, in that structure, each of the carbons will be sp2 hybridized because they have a double bond. Because it's sp2 hybridized, they're going to have p orbitals. They're all going to be perpendicular to the plane of the molecule, and therefore they will all overlap. You've got, in this case, 6 p orbitals overlapping. So in fact, you're going to have 6 molecular orbitals. And here are those 6. Now this is technically benzene, but if we replaced one of the carbons with a nitrogen, you'd get that. And so it doesn't really change anything, but we have in pi bonds, there's 1, 2, 3 pi bonds. Each bond is 2 electrons, so there's 6 electrons in pi bonds, essentially. Therefore, there's 6 isolated electrons there going into these 6 molecular orbitals. You see one, I should probably change the color here, 1 node in these versus 0 nodes here. And there's going to be 1 and 2 nodes for each of those. And 1, 2, and 3 nodes in that one. Turns out that these are bonding, those are anti-bonding, and you got the 6 electrons, and you see they're all in bonding. And so the 6 electrons in benzene or in that pyridine, they're going to be spread out throughout the whole molecule. So you'll see drawings for benzene or pyridine where you have these isolated double bonds. I could even have a resonance structure where the double bonds are in different locations by saying, hey, that moves there, this moves here, and that moves there to make that. Excuse me. In reality, because you got these 6 electrons in 3 different orbitals that are encompassing all 6 atoms in the ring, the real drawing for benzene should be more like this, where that middle circle is representing the 3 double bonds encircling the entire interior in those, overlapping p orbitals. And so they're creating this like hamburger shaped thing there, but above and below the plane of the flat molecule. But that's what you get for benzene. So electrons are really delocalized through the whole atom. These last ones happened to have electrons in p orbitals that are going through the whole thing. But I do want you to know that this works for everything. If there's no p orbitals, if it's something like ethane even, ethane is C2H6, we could draw its structure like this. And there's 2, 4, 6, 8, 10, 12, 14 electrons. All 14 of those electrons are spread out through the whole molecule, and pretty evenly so. We're not going to get into the complicated drawings of those, but stuff like what we see here with benzene and the one before it with pyridine, those are relevant when you get to organic chemistry. So if you go to that class, you will see this stuff again, because it does become important when we're discussing why certain reactions happen and why others don't. All right, that is it for Chapter 10 and Unit 3. So again, your test is going to be Monday during lab time on Chapters 9 and 10. Check Canvas for a practice test. I have put it up. It'll be there, and the answer key to that will go up Sunday night. If you have any questions, don't hesitate to email me or send me a message on the Remind app.